This session is about zeros and multiplicity, and to start this topic we're going to recall how to solve an equation like x squared minus 5x minus 14 is equal to 0. We would first factor the expression on the left hand side, x minus 7 times x plus 2, and then setting each factor equal to 0, come up with the solutions, or zeros, x equals negative 2 or 7. The point of this is that factors and zeros are closely related. Multiplicity refers to factors, and therefore zeros, that are repeated. Let's see what that means. Our first example, find all real and imaginary roots, stating multiplicity when it is greater than 1. Roots, zeros. There's a lot of variation in terminology here. Roots are essentially solutions to equations. The equation is x squared plus 6x plus 9 equals 0. I recognize the expression on the left-hand side as the square of x plus 3, so I actually end up with x plus 3, the quantity squared, is equal to 0, and so x is equal to negative 3. But because the x plus 3 had a squared exponent, the exponent was 2, x equals negative 3 is a 0 of multiplicity 2. Yeah, it's that straightforward. Multiplicity refers to the exponent on a factor. We don't really ever say multiplicity is 1. Why would we do that? Next, find all real and imaginary roots, stating multiplicity when it is greater than 1. Here we have 2x plus 1, the quantity squared, times x minus 5, the quantity cubed, is equal to 0. Oh, Christmas has come early. This is already factored for us. The first factor, 2x plus 1, the quantity squared, gives me that x is equal to negative 1/2. And this is a 0 of multiplicity, can you guess? 2, because the exponent's 2. The second factor gives me that x is equal to 5. And that is a 0 of, anybody? Multiplicity 3. So let's go back to the previous example here. X squared plus 6x plus 9 is a degree 2 polynomial. The biggest exponent is 2. The 0 is multiplicity 2. Okay, back to our current example. 2x plus 1, the quantity squared, x minus 5, the quantity cubed. If we were to multiply this out, we would end up with a degree 5 polynomial. You can go ahead and do that. I'm going to leave it to you. Check it out, the multiplicities. Multiplicity 2, multiplicity 3, they add up to 5. That's going to be characteristic of all polynomials. The number of zeros, counting multiplicities, equals the degree of a polynomial. Believe it or not, that's actually a consequence of something called the fundamental theorem of algebra. Where this is going to show up for us is down the road when we consider graphing polynomials. So what I'd like to do is consider y equals x minus 3, the quantity squared, and y equals x plus 2, the quantity cubed. Well, yeah, okay. For the first one, x equals 3 is a 0 of multiplicity 2. For the second one, x equals negative 2 is a 0 of multiplicity 3. What I want to do is talk about why multiplicity is important as far as graphing is concerned. It actually indicates the behavior of a graph at a 0. To see how that works, we're going to look at quick sketches of each of these functions. So, y equals x minus 3, the quantity squared, would be a parabola whose vertex is at 3, 0. And y equals x plus 2, the quantity cubed, is a cubic function with the wiggly part at negative 2, 0. Let me just label the axes real quick because the little voices are telling me I have to. I see for y equals x minus 3, the quantity squared, we have a graph that bounces off of the x-axis at x equals 3. And we're going to refer to this as touching the x-axis. Alternatively, when the exponent is 3, as in y equals x plus 2, the quantity cubed, we have a graph that crosses the x-axis at that 0. And it's actually going to be the case that for any factor that is repeated, if the multiplicity is even, then we're going to touch the axis at that 0. If the multiplicity is odd, then the graph is going to cross the x-axis at that 0. So we can kind of make a Frankenstein function out of these two. Y equals x minus 3, the quantity squared, times x plus 2, the quantity cubed. And what we would find, and this is for another session, but I'm setting things up, is that at x equals 3, we would touch the x-axis. At x equals negative 2, we would cross the x-axis, again thinking of it kind of as a Frankensteining of these two, and we would end up with a graph that looks something like coming up from the right, down, bouncing off of the x-axis at 3, and then crossing the x-axis at negative 2. Technically, there would probably be a little bit of a wiggle when it crosses the axis at x equals negative 2, but I'm not really going to hold you to that. What I need you to know is that at a root of even multiplicity, we're going to bounce off the axis. At a root of odd multiplicity, we're going to cross the x-axis. And then the other place that multiplicity is going to come up is going to be in forming polynomials, which I'll record in a few minutes.